Okay, so yesterday we talked about significant figures, and I showed you how to do the calculations. There was a couple of things that I did leave out on purpose, and that was one, if you were doing math operations that involve both addition and subtraction and multiplication and division, the multiplication and division rules trump the other rules, okay? So that's something to keep in mind, because occasionally we will do those types of calculations where you have mixed operations, but multiply and divide, it trumps the other ones, okay? The other thing is we're fixing to start talking about conversion factors, okay? And when we are doing these conversion factors, if it is an exact number or it's a known conversion factor, it will not affect the determination of how many significant figures to put your answer in, okay? In other words, I know that there are 12 inches in 1 foot, okay? The 1 foot that's an exact conversion, so I would not use the one significant figure in 1 foot to indicate how to report my measurement, okay? So you're always going to use the measured value to indicate your level of precision, okay? So if I give you a problem and I say there's, 48.7 grams, then you're going to use the 3 significant figures in the measured value, okay? Never use your conversion factors, because next unit we're going to get to a conversion that's going to be grams per 1 mole, and it's always going to be per 1 mole. We would not say then I only report my answer in one significant figure. So if it's a conversion factor, you're not going to use that to determine that. I left that out yesterday because we weren't doing any conversions and it just would have muddied the water a little bit. So I want to make sure we know that. And I will repeat that as we're going through, because it's a common mistake, so people will make that and I'll say we don't use our conversion factors to determine our significant figures. Okay, so you kind of already saw about the metric system in the video. And so right now I'm going to tell you what we use in here mostly, okay? And these are the standard SI units. That means they're the accepted units in science. All right, well, they were adopted in 1960. And here they are. Okay, so for mass, we will be using the kilogram. That is actually we'll use the gram more than we do the kilogram, but the kilogram is the accepted SI unit. And I guarantee you someone will miss that on a test because they'll tell me it's grams. Because we use grams in here more often because we're dealing with smaller quantities. But it is actually the kilogram that is the accepted SI unit. Okay? For volume, we will be using the liter as the accepted unit, but oftentimes we will be using the milliliter because we're dealing with smaller quantities. But the accepted unit is the liter. Excuse me, length is meters. Excuse me, temperature is going to be actually Kelvin, which is a big K, and there is no degree sign there. Okay? Most of the time we're going to measure things in Celsius and use Celsius, but the accepted unit of measurement is Kelvin. And then mine's left off, but on yours you have time is the next one. And that's going to be in seconds. And here is where another commonly missed test question. We abbreviate seconds as an S, not SEC. Okay? Most of you are used to doing it in SEC, and that's how minute is MIN. But in science, it's just an S, okay, as the way you represent it.
Time isn't measured any different anywhere else, right?
No, it's just that second is what we use instead of using minutes or hours or whatnot, okay? When we come to the metric system, we have these prefixes that we will use, okay? That's what makes the metric system so convenient for our use. Oops, too far, sorry. Is that we can add prefixes to them so that we don't have to deal with very, very large numbers or very, very small numbers. So we put a prefix on there, okay? This is the equivalence of them. We're going to actually use them a little bit differently because it's easier for us. For instance, I can remember whole numbers better than I can decimals. So we're going to use that there's 100 centimeters in a meter rather than there's 0.01 meters in 1 centimeter, okay? If you want to use it the other way, you can. These are the most common ones that we will use in here. The ones in the box on your notes are the ones we use all the time that you must memorize. So put yourself a little note to say memorize the ones that I have in that little separate box. And if you notice, I put those in whole numbers, okay? I put that there's 10 decimeters in 1 meter instead of 0.1 meters in a decimeter. Most brains think better in whole numbers than decimals, okay? So you do have to memorize those. If it's one of those, I will not give it to you on a test. I'll expect you to know that there's 1,000 milliliters in a liter, okay? But if it's another one like picometer or that, unless I tell you specifically, usually I give that to you, okay? But those are the most common. There's actually more than that. Those are just the ones that show up the most. These are actually all the ones that there are, okay? Some you've probably never heard of. I would imagine you've heard of Giga and Tera, and where have you heard of that for? Computers, gigabytes and terabytes. So a gigabyte is 1 billion bytes. A terabyte is 1 trillion, okay? And mega is 1 million. But it goes pretty far, you know, as far as that. These are just some examples of some things that you can kind of visualize what these are. So like if you had one water molecule, it would weigh 1 times 10 to the negative 24 grams. That means there'd be 23 zeros in front of it. So it's very, very small. And of course the Earth would have 24 zeros behind it for its mass, okay? Whenever we're using those prefixes, I want to make sure that you understand it's the same prefix whether you're talking liters, meters, grams, okay? It's all the same. I want to go back to that and make sure you understand this part, okay? So this right here is where your base unit is, in the middle, okay? This is your base unit, liters, meters, grams. Can be other things too, like you can have a millisecond, you can have a nanosecond, but we don't do that as often. Those are the 3 things that we use the most. If it is up here, it is smaller than the base unit. In other words, it takes a lot of them to equal the base unit, okay? If it's on the other side of it, it's bigger than the base unit. In other words, for a kilo, it takes 1,000 meters to equal 1 kilometer because a kilometer is bigger than the base unit of a meter, okay? If it's a centimeter, it's smaller, so it would take 100 centimeters to equal a meter, okay? Or liter or gram. I want to make sure you understand that. We use those, the reason I use the whole numbers is because there's already things in our world that we can relate to. For instance, a century, how many years are in a century? 100, okay? Because we kind of already know that. How many years are in a millennium? 1,000, and then a decade is 10. So those are things we kind of already know for equaling the, you know, the prefix, so to speak. Okay, so I want to make sure you understand that. Okay, these are just the examples of the ones in your box that I want you to memorize, and it is very important that you memorize that. Okay, this is that right there. Those prefixes are in your box. The 10 to the 6, how many is that really? If I was to write that out in non-scientific notation, how many would that be? 1 million. It's 1 million. It is 1 million. 10 to the 6 is 1 million. Okay? So then if you go 10 to the 9th, go up by 3, that's a billion. 10 to the 12th, like that. Okay? Yes. All right? The derived units are units that they take those accepted SI units and they do a calculation and they get these derived units. They're not technically under that SI system, but it's what we will be using. For meter squared, where do you think that is? Anybody want to guess? Area. Because area, how do we determine area? Length times width. So a meter times a meter would give us meters squared. The grams per centimeter cubed is going to be density. Okay? And then volume, we can use a centimeter cubed or milliliter. You also must memorize this. You will use this throughout the year, that a centimeter cubed is equal to a milliliter. Okay? Also, a liter is equal to a decimeter cubed. Okay? So those are things we have to memorize. Temperature. We must be able to convert between Celsius and Kelvin. You'll be doing that throughout the year. It is the easiest calculation we do in here. We literally take the Celsius temperature and add 273 to it. That's it. Okay. Technically it's 273.15, but for our purposes we can just say 273. Okay. AP, I usually make them throw in the 0.15 back in there, but for here we can just do 273. 0 degrees Kelvin is absolute zero. It's a temperature where all molecular motion ceases to exist. Remember in the matter unit we said even solids vibrate in place, but if you actually reach 0 Kelvin, it ceases. And theoretically at that temperature there's no volume because there's no particle movement. It has not been reached. Okay, I knew that was going to be a question. It has come very, very, very close. There's a really interesting YouTube video on how they're trying to reach it. But the thing is there always will be a tiny bit of motion. So they maybe get like 0.0005 Kelvin. You know, they've gotten really close, but and you can't, there's nowhere on the Earth or the planet or the universe that it exists on its own. They're having to physically make it get to that. Okay, I put the Celsius to Fahrenheit conversions in there so you could see them. In years past, the pre-AP students were required to convert between Celsius and Fahrenheit. I don't see the necessity to do that, especially because nowadays with our phones, if we wanted, we would just literally say, Siri, what is 78 degrees Fahrenheit in Celsius, and it would tell you. And we measure nothing in here in the F word. All of our Fahrenheit, yeah, all of our thermometers are going to be Celsius, so it's not going to be. It's something that they would do on the test and then never do again. So I'm not going to make y'all do it. Okay. So if you're ever working a worksheet and it's asking you and it gives you a Fahrenheit temperature, just assume that it's a mistake and change it to Celsius automatically. Okay. Just assume that it's a typo or it's just an old worksheet and we never fixed it. So change any temperature you see that's in Fahrenheit. Just put it in. Just change it to a Celsius. Okay. This right here is, I said it earlier. This blank is there is no degree sign is used for Kelvin temperature. So we're used to saying degree Celsius or degree Fahrenheit, but like if I was going to say something, I would say like this, just a K, a big K, by the way. Okay. Just to kind of give you an idea of how they relate to each other, water freezes at 32 degrees Fahrenheit, 0 degrees Celsius, and 273 degrees K. So that just kind of gives you an example or something to relate that to, because most of us are used to thinking in Fahrenheit temperature. Okay, so I need you to start thinking in Celsius. Water boils at 100 degrees Celsius, which is 212 and 373 K. Okay, so that's just what that looks like. And then that's where we're going to stop. We're going to do dimensional analysis tomorrow.